Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today's topic of discussion is parallel AC circuit analysis. Our objective is to introduce fundamental parallel AC circuit properties and examine parallel AC circuit analysis techniques like Kirchhoff's current law. Additionally, we'll examine the influence of shorts and opens inside parallel AC circuits. Bottom line up front, parallel AC circuit analysis is parallel DC circuit analysis using phasors. I cannot make it much simpler than that. This lecture therefore operates under the presumption the viewer is intimately familiar with fundamental parallel DC circuit properties as illustrated in the Basic Electronics 1 DC Circuit Analysis playlist, available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. Additionally, it is presumed the viewer has ample experience with complex numbers, phasor representation of AC quantities, and Ohm's law as it pertains to AC circuit analysis. If there is the slightest hesitancy on your part regarding any of these topics, go away and do not come back until you have mastered these subjects. If you feel you are among the worthy, let us begin. Let's explore basic parallel AC circuit properties in terms of impedance, current, and voltage distribution. Let's first examine parallel impedance. As you're no doubt aware, the complex impedance of a parallel or side-by-side configuration of elements can be calculated using two different techniques, as illustrated in the parallel complex impedance lecture, available at the Big Bad Tech channel. One formula states the total impedance of a parallel relationship of two elements is Z1 times Z2 divided by Z1 plus Z2. The second formula states that 1 over the total impedance of a parallel relationship of any number of elements is 1 over Z1 plus 1 over Z2 plus 1 over Z3, and so on. Consider a parallel combination of two elements. The first element is a 500 ohm resistor, and the second element is a 10 microfarad capacitor. The sinusoidal AC voltage source has an effective value of 120 volts and an excitation frequency of 60 Hz. The complex impedance of the 500 ohm resistor is 500 ohms at an angle of 0 degrees. Let's call this impedance Z1. Note Z1 is pointed entirely in the horizontal positive real direction. Complex impedance of the 10 microfarad capacitor at an excitation frequency of 60 Hz is roughly 265.3 ohms at an angle of negative 90 degrees. Let's call this impedance Z2. Note Z2 points entirely in the vertical negative imaginary direction. Using either formula, total impedance for this parallel network equals 234.3 ohms at an angle of negative 62.1 degrees. You note that the negative angle of total impedance indicates the complete parallel circuit will exhibit largely capacitive behavior. Let's put these impedance values aside and examine voltage distribution in parallel AC circuits. As you are no doubt aware, voltage is a two-point measurement. As such, voltage across elements in parallel is the same. This is the most fundamental parallel AC circuit property. Given the source establishes a differential of 120 volts between the top and bottom node of this parallel circuit, resistive impedance Z1 experiences a differential of 120 volts, as does capacitive impedance Z2. E equals V1, which equals V2. If we know the voltage across any parallel element, we by extension know voltage across all remaining elements in parallel. I say again, voltage across elements in parallel is the same. This is the most fundamental parallel AC circuit property. Let's now examine current distribution through individual elements within this parallel AC circuit and source current. Given known impedance values and known voltage values, it's possible to directly solve for current through each individual element using Ohm's law, which states current is equal to the voltage divided by impedance. An application of Ohm's law for resistive impedance element Z1 demonstrates I1 to be 240 mA at an angle of 0 degrees. The phasor diagram demonstrates current through purely resistive impedance Z1 will be in phase with the voltage across it. An application of Ohm's law for capacitive impedance Z2 demonstrates I2 to be approximately 452.4 mA at an angle of 90 degrees. The phasor diagram demonstrates current through capacitive impedance Z2 leads the voltage across it by 90 degrees. Note the parallel impedance with the largest magnitude, in this case resistive impedance Z1, draws the smallest amount of current. Conversely, you'll know the parallel impedance with the smallest magnitude, in this case capacitive impedance Z2, draws the largest current magnitude of 452.4 mA. Let's now examine source current. Kirchhoff's current law states that the summation of all incoming currents must equal the summation of all outgoing currents. What goes in must come out. As we previously demonstrated using Ohm's law, resistive impedance Z1 draws 240 mA at an angle of 0 degrees from the source, and capacitive impedance Z2 draws 452.4 mA at an angle of 90 degrees from the source. It should be self-evident that the source must therefore supply 240 mA at an angle of 0 degrees, plus 452.4 mA at an angle of 90 degrees, or 512.1 mA at an angle of 62.1 degrees. IS equals I1 plus I2. The phasor diagram demonstrates source current will lead supply voltage by 62.1 degrees. This leading phase angle is to be anticipated given the somewhat capacitive nature of our total impedance. As a means of checking our work, one can also solve for source current using our previously calculated total impedance. Ohm's law states that source current will be equal to supply voltage over total impedance. Substituting in our given values yields source current to be approximately 512.1 mA at an angle of 62.1 degrees. I've got a reasonable degree of confidence our earlier answers are correct. It's worth mentioning that any algebraic rearrangement of the Kirchhoff's current law equation for this parallel circuit allows us to directly solve for unknown current values or as an alternate means of checking our previous calculations. For example, if we knew source current and I1, we could algebraically rearrange these values to solve for unknown current I2. An algebraic rearrangement of the Kirchhoff's current law equation for this parallel circuit, solving for I2, suggests that IS minus I1 equals I2. Substituting in our calculated values for source current and I1 yields I2 to be 452.4 mA at an angle of 90 degrees, doubly confirming our earlier calculations. Before moving on, it may be helpful to remind ourselves what phasors represent. Recall that phasors are simply shorthand representations of more complex time-variant sinusoidal phenomenon, conveying the most pertinent information, notably RMS or effective value, and the degree of phase shift in a compact and convenient format for the purposes of calculation and algebraic manipulation. If we represented supply voltage as a time-variant phenomenon, it would look something like this. Supply voltage with an effective value of 120 volts would peak at roughly 170 volts. A waveform with a frequency of 60 Hz would sinusoidally alternate over a period of 16.7 milliseconds. Source current with an effective value of 512.1 mA would peak at roughly 724.2 mA. Source current also sinusoidally alternates every 16.7 milliseconds. Source current appears to lead supply voltage by roughly 2.9 milliseconds, the equivalent of 62.1 degrees. Source current essentially splits into two paths, one traveling through resistive impedance Z1 and the other traveling through capacitive impedance Z2. If we were to add a plot of current through resistive impedance Z1 as a function of time, it would look something like this. I1 appears to be in phase with the supply voltage. If we were to add a plot of current through capacitive impedance Z2 as a function of time, it would look something like this. I2 appears to lead supply voltage by 90 degrees. Note at any instant in time, the summation of instantaneous currents drawn by the individual parallel paths do in fact equal the instantaneous current supplied by the source. It's moments like these which truly convey the utility of phasor diagrams. Yes, one could take the time to painstakingly plot and interpret all these electrical properties as a function of time. However, phasor diagrams convey the same information in the smallest possible space in a far more readable fashion.